So tying back into our section 3, where in section 3 we talked about dependent events. So when we talk about independent events, we talk about the ability that there's no relation between two or more events. So meaning one event can occur and a second event is going to happen in a very similar fashion, just without any kind of reliance on the first one. Very different types of situations. Now tying back into section 2, when we talk about mutually exclusive and non-mutually exclusive events, we do have to remember some of our terminology. For example, if we are using the word or, it means that we're talking about the union of events. We have the probability of one thing occurring, adding the probability of a second thing occurring, subtracting the probability of them both occurring. So when we have something that can have any kind of overlap. At the same time, in our last section, we actually were using the phrase and, which is a probability of A and B happening, being the probability of A happening multiplied by the probability of B happening, given that A has already occurred. We have to keep both of those formulas in mind as we're working through this question. Example 1 is showing that one card is drawn from a standard deck of cards and being returned to the deck. The deck is reshuffled and a second card is selected. We're going to find the probability of the following situations. The biggest thing that we need to keep in mind is that we are returning the deck to the card, or the card to the deck, meaning we do have independent events. One card being drawn and then a second card being drawn. Well, because it's being returned to the deck, whatever the first card was, it has no impact on what the second card is. Whereas if we did return it to the deck, then we'd have to be dealing with a different situation. So let's find out the probability of following. 2 red cards. Well, that actually means that we have a red card and a red card happening. And because of that, and being a good example of this multiplication. So if we want to find out the probability of A happening, so 2 red cards being drawn, probability of A and B happening, probability of A multiplied by the probability of B, given that A has already occurred, well, our probability of A, so the probability that the first card is red, how many red cards are in a deck? Well, there's diamonds and there's hearts, which means that there's 26 out of the possible 52 being multiplied by the probability that the second card is red. But since we've returned that first red card to the deck, we'd have 26 cards in the deck. Now that we're going to multiply them, means that we should also probably reduce them. 26 and 52 would reduce to be 1 and 2. 26 and 52 reduced to be 1 and 2. 1 by 1 is 1. 2 by 2 is 4. There will be a 1/4 probability, 1 out of 4 chance, that we could draw 2 red cards. And actually, that could be beautifully done as a Punnett square for those of you that have already done some bio. Because we have 2 situations. Actually, let me just fill in the rest of this chart. Because we're drawing 2 cards, well, here's a chance. The first card could be blue. And the second, well, actually, let's go this way. There's the first, there's the second. The first card could be blue. Black, sorry. Which means first card would be black. Second card could be black. Well, the first card, if it was black, the second card could be red. First card being red. Second card being black. And here's our chance. Here is our 1 out of 4 chances that we could draw a red card and a red card. 1, 2, 3, 4. 1 out of those chances. If we're talking about it being odds, it'd be 1 to 3. B. What's the probability of drawing 2 aces? Now I'm going to skip drawing down the formula because we can just refer back to it. What's the probability of the first card being an ace? Well, there's 4 aces in a deck out of a 52 card deck. What's the chance that the second card is an ace? Well, there's still 4 aces if we return it to the deck out of the total 52. And then if we further reduce, 1, 13, 1, and 13, there would be a 1 out of 169 chance that we'd have 2 aces. How about C? What's the chance of having an ace, then an 8? Well, to have an ace and an 8, chance that the first one is an ace is 4 out of 52. The chances that the second one is an 8. Well, there's 4 8s in a deck out of a total of 52. We've already done that exact same calculation. We know that's going to come out to 1 out of 69. Make it look like a 9. Sorry, I'm going to have to erase that. So therefore, we have that same kind of probability. Now what about D? An ace and an 8 in either order. So meaning we could have an ace, then an 8. So there's our ace probability, there's our 8 probability. Well, if it could be either order, it means that we could also have an 8, then an ace. And since we can have that probability, the probability of it being 8 first, being multiplied by the probability of the second one being an ace, what we're going to do is we're going to add those probabilities. Now, since we already know what those will reduce down to be, being 1 out of 169, probability of having an ace and an 8 drawn in either order will be 2 out of 169 chances. So if you were to shuffle the deck, you'd have an ace and an 8, or an 8, then an ace, occur 2 out of 169 shuffles. And next question. A die is rolled 3 times. Find the probability of rolling a 6 each time. So what's our probability of the first one rolling an ace? Or sorry, 6. Rolling an ace. Jeez. There's 1 out of every 6 chances that we'd have 6. Now we're going to multiply. Well, if we're rolling 3 times, chance of the second one's being an 8, being a 6, 1 out of 6. Third one being a 6, 1 out of 6. Meaning, multiply everything together, we get a 1 out of 216 chance. Oh, sorry. How about B? What's the probability of never rolling a 6? Well, how many times are you never going to have a 6? There's a 1, 2, 3, 4, or 5 that are not a 6. every single roll, which means never rolling a 6. We 125 out of 216. So again, that is never rolling a 6. Never rolling a 6. So what would be the probability of rolling at least 1 6? Well, that's a little bit of a different terminology than we've dealt with before. At least. At least means that you can have 1. Could be 2, or it could be all 3. So you could have 1 6, you could have 2 6s, or you could have 3 6s. You are just not going to have no 6s. So if you're not going to have no 6s, this is our probability of having no 6s. Now the beautiful thing is 100% probability means it's going to happen. So if we know that if we have 216 rolls out of 216, that's 100%. If we subtract off the probability of never rolling a 6, it means that we'd actually have at least 1 6. Which means there'll be 91 chances out of 216 that you could have at least 1 6. This 1 out of 216 would be the chances of them all being a 6. So that means that there will be 90 chances that you could have either 1 or 2 6s rolled. And D. Each roll results in a number less than 5. Well, how many numbers are less than 5 on a die? 4. And it says each of these rolls. And the beautiful thing, let's reduce them. So 4 and 6 reduces to be 2s and 3s. Each and every single one of them. Eight out of 27. The reason that we stick with reduced fractions is because it's going to be a lot easier to really have the full probability. Absolutely, this is the exact same thing as 64 out of 216. But why say that you are going to have 64 out of 216 times that each roll is going to result in a number less than 5, when you can just say, oh, 8 out of every 27. It's just a lot better and a lot more condensed. It makes everything a lot easier. All right. Example 3. 99% of computers manufactured in a plant have satisfactory keyboards, which means the keyboard works. Or at least good enough that people are going to be happy with. And 96% of the computers have satisfactory monitors, so what you actually look at. If you purchase a computer, determine the probability that it will have a satisfactory keyboard and a satisfactory monitor. So again, we're dealing with this phrasing of and. The phrasing of and, well, we're going to multiply those probabilities. So for A, satisfactory keyboard is 99%. Of course, 99% is going to be a lot easier to deal with it as a decimal. And we multiply it by the probability of having a satisfactory monitor, which is 96%. You multiply them together, and you'd have 0.9504, which absolutely will be 95.04%. B, a satisfactory keyboard and an unsatisfactory monitor. Well, we know what a satisfactory keyboard is. It's 0.99. But what's the probability of having an unsatisfactory monitor? Well, if 96 are satisfactory, which means that they actually work, there's 4% left that's unsatisfactory. So 0.04. Multiply that out. And you get 0.0396, which is 3.96%. Continuing on, an unsatisfactory keyboard and an unsatisfactory monitor. Well, unsatisfactory keyboard occurs 1% of the time. An unsatisfactory monitor occurs 4% of the time. We get 0.0004, which would only occur 0.04% of the time. D says a satisfactory keyboard or a satisfactory monitor. Oh, that's interesting. We need to know what's our probabilities here. Well, here's our keyword, or. The formula for or is this additional probability. It's going to be the probability of A or B happening equaling the probability of A, add the probability of B, subtracting the probability of A and B happening. So what's the probability that we have a satisfactory keyboard? Well, I think it should be 99%. What's the probability of having a satisfactory monitor? 0.96. Subtracting the probability of having a satisfactory keyboard and a satisfactory monitor. Well, that was a great thing. We just calculated that out. Having both of them being good is 95.04%. Oh, sorry, extra decimal. You add and subtract everything together, you get 0.9996, which means it's a 99.96% chance that you have a satisfactory keyboard or a satisfactory monitor. Now, of course, if you're dealing with a desktop and you're trying to actually buy this, that's still not very good. Because we want to have a satisfactory keyboard and a satisfactory monitor. We don't want to have to replace one or the other. This 95%, probably not the greatest thing, meaning that the company is going to have to do a little bit of maneuvering and get things going. Now, of course, there's an alternate way of doing this. Having a satisfactory keyboard or a satisfactory monitor just means that one of them is good. So if one of them is good, it means that they both can't be bad. If we took a full 100% and subtracted off at 0.04, sorry. We'd still get that 0.9996, which is the 99.96%. So it still does work. Sorry, I guess this is incorrect. It should be 0.000. But I think that you can get my point. Now, just as a fun bit of information, those three things, having a satisfactory keyboard, satisfactory monitor, satisfactory keyboard, unsatisfactory monitor, unsatisfactory keyboard, and unsatisfactory monitor, well, you add up all these percents, you only get 99.04%. Because it's not including the fact that we could have an unsatisfactory keyboard but a good enough monitor. Now, obviously, if we can look at it, we know that that answer should be 0.96%, but we could calculate that out because having an unsatisfactory keyboard but a satisfactory monitor, well, the keyboard would be 0.01. You multiply it by having a good enough monitor, it would be 0.096. It would be 0.0096. So all of these things together adds up to be 100%. Right. I'll get out my deviation. A coin is tossed 5 times. Find the probability of tossing 5 heads in a row. So you go flip. Oh, what's the chance of the first one being ahead? 1 out of 2. What's probably the second one being ahead? 1 out of 2. What's probably the third one being ahead? 1 out of 2. These are independent events. They are the situation where one thing does not have a bearing on the second, doesn't have a bearing on the third, doesn't have a bearing on the fourth, doesn't have a bearing on the fifth. You multiply it out, you get 1 out of 32. Shoot, we see this phrasing again. At least one tail. Well, what does that mean? Having at least one tail means you could have 1 tail, 2 tails, 3 tails, 4 tails, or 5 tails. You just cannot have 0 tails being tossed. Or where does that lead? We just can't have this situation. We can't just have all heads, which means we'd be taking 100% and subtracting the probability of them all being heads. So in a fair situation with a fair coin, the probability that if you were to toss 5 times and you'd have at least 1 tail would be 31 out of 32. At the same time, having the probability of them all being heads will be 1 out of 32. Now, you could spend all the time and calculate it out. Of course, experimental probability is usually very different than theoretical. Though, if you do things enough, typically what does happen is that experimental probability does start bordering on being the same as theoretical. All right, I think we only have the 1 question left. Awesome. Okay, so if the probability that a batter gets a hit is 0.300, known as a batting average, common phrasing is you could be batting 300. Formula for statistics or statisticians being able to calculate this, it's just the number of hits just takes and divides it by the number of times that a person is at bat. We're going to find the probability that we get that in 4 times at bat, the batter gets 4 hits, no hits, 1 hit, at least 1 hit, exactly 1 hit, exactly 2 hits. Let's do some calculation. What's the probability of having 4 hits? Well, if we're batting at 300, that's our probability. Now, of course, some of you may start saying, oh, how they do in the first hit may affect how they are going to do in the second hit, and the third and fourth. This one is just kind of a more theoretical situation where your slate is completely wiped clean after every single hit, or no hit. So the probability of the first one being a hit is 0.3. Probability of the second one being a hit, 0.3. Third one being a hit, 0.3. Fourth one being a hit, 0.3. Which means This is tying back to our grade 9, 0.3 to the power of 4. And if you type that into your calculator, you get 0.0081 or 0.81%. So it's not even a 1% chance that someone who has a batting average of 0.3 gets a hit 4 times in a row. Because especially if you're playing baseball and you're just playing in a kind of competitive nature, of course it's going to be very difficult. At the same time, someone who has a batting average of 300 is considered to be very good. What about having no hits? So no hits means you're not getting a hit. No hits in 4 times at bat, well, to not get a hit will be 0.7. Not getting hit 4 times in a row will be 0.7 to the power of 4, which is 0.2401, or 24.01%. Now that's obviously a very much higher percentage. They have a 24% chance of not getting any hits at bat. Again, competitive nature and everything that rides along with that. But it's much more likely that that's going to happen. At least one hit. Well, what's the terminology for at least one hit? In other words, it's not no hits. So if I took 100% and I subtract off my probability of having no hits, make that actually look right. We come down to this situation where we'd have a 75.99% chance of getting at least one hit. So meaning that you could have 1 hit, 2 hits, 3 hits, or 4 hits. And of course, we can calculate exactly what those would be. So therefore, if we want to find out what is the probability that 4 times at bat the batter gets exactly 1 hit, well, we're going to calculate it very similarly to what we've done already. Well, the probability of one hit would be 0.3. Now there's only going to be one of those, multiplied by 3 non-hits. Now the only issue though, now I'm just going to write this out, that's going to give us probability of 0.1029 or 10.29%. But that's not the only chances. What we're really dealing with is probability that he or she could have a hit, miss, miss, miss. Or could miss the first time he's at bat, get a hit the second time, miss. Could have a miss, miss, hit, miss. Could have a miss, 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 hit. Which means that there's 4 options for getting exactly 1 hit. And it's a good thing that we've actually done this exact same situation before. It's actually dealing with our combinations, or combinatorics, sorry. It's our permutation. More specifically, it's a permutation with repeating objects. We have a total of 4 times at bat. 1 time is going to be a hit, 3 times are going to be a miss, which means we're actually going to take this 0.1029 and multiply it by 4 to give us what the total percentage would be. Total probability that this person would get exactly 1 hit. So that comes out as 0.4116, or a 41.16% chance. Alternately, if we're looking for exactly 2 hits, well, same kind of procedure. 2 hits, 2 misses. Now I'm going to leave this open. That's going to give us a 0.0441, or 4.41%. At the same time, knowing that there's 2 hits and 2 misses means out of a total of 4 times at bat, 2 are hits, 2 are misses, and we're going to multiply this by 6. 0.0441 multiplied by 6, 0.2646, or 26.46%. Just to finish it off, this is completely alternately, but if we were to go for exactly 3 hits, it'd be the exact same kind of procedure. 0.3 to the power 3 and 0.7 to the power 1, having 4 times at bat, 3 times are hits, 1 time is a miss. Well, 0.3 to the power 3 times 0.7 to the power 1 comes out as 0.0189. 4 factorial divided by 3 factorial. 1 factorial is 4. So all of that calculates out as 0.0756, or 7.56%. Just to finish everything off, if we are talking about 4 times at bat, the probability that they're going to get 1 hit is 41.16%. Probability of getting 2 hits is 26.46. Probability of getting 3 hits, well, we just calculated that out as 7.56. Above, we calculated for 4 hits. It's 0.81%. So 1 hit, 2 hits, 3 hits, 4 hits comes out as 75.99%, which exactly is what happens of getting at least 1 hit. If we add our no hits, which means we add the 24.01, we get a 100% chance.